Oxygen at a temperature of 27 is maintained at a pressure of 2 atmospheres. This gas is flowing over a 50 by 50 centimeter plate held at 127 Celsius. The free stream velocity of the gas is 30 meters per second, and you can assume that the square plate is isothermal. Its temperature is not changing, right? It's going to be the same throughout. What is the total heat loss of the plate in watts? Okay, so the question is pretty straightforward. The question is, what is Q, right? Let's just go over some important things here. Oxygen, first thing is oxygen. So I know it's silly, but you guys, a quarter of you guys would use table A5 for air, even though it's oxygen, it's not air. Temperature of 27, that's fine. And then the pressure of 2 atmospheres, right? So this is a big red flag here. Because we know some of the things we need are they change, right? They're sensitive to pressure. The gas flowing over is 50 feet, that's fine. Held at 110, that's fine. The free stream velocity is 30. Why did I say free stream? Because it's not going to change when it encounters a plate. We could make these problems more complicated if you had to consider more things around the mechanical fluids, but you don't, okay? So it's traveling at 30 and then it finds a plate, it's still at 30, it goes at 30 the whole time. It doesn't change. What is the total Q, okay? So we know Q is going from the plate to the air. We know that already because the plate is at a higher temperature. And we know we're going to have to find properties. We know that when the oxygen touches the plate, it will begin to heat up. Because we know the temperatures are changing, we're going to get the T film, right? So we're going to get the average between the two of them so that we can find the properties of oxygen on the average. So if I sum them both up, divided by 2, I get 77 Celsius, which is 350 Kelvin. So you'll note that you have the oxygen table, property table on the second, it's the second table on your question sheet. So we can go ahead and grab the properties for oxygen at 350.
Sorry, Pablo, just quickly.
Yep.
On TF, is it 127 and 27?
Yes.
Yeah.
127 and 27.
Shouldn't it be divided by then 102, not 77?
Sorry, what's that?
Shouldn't it be 127 and 27 is 204 to, 154. Did I make a mistake? I did, sorry, my bad.
Cool, no worries. No worries, make mistakes, that's how you guys learn. That's the best thing, okay? So what I'm gonna do is I'm gonna grab the properties for oxygen at 350 and I'll lay them all down here and then we're gonna account for the 2 atmospheres, okay? So you guys can go ahead and do that with me. I'll pause the video. So we have the properties and then we know that out of these guys here, none of them are pressure dependent except this guy here, right? And what you can do is you can jump back to the video on the Reynolds number if you wish, in which I explain how you guys can account for that. But since I did that already in the video, we know that the pressure, let's do it like this, since P equals 2 atmospheres, then density equals 2 times density, which is just 2 times 1.1133 kilograms per meter cubed. Okay, so that will be our density with 2 atmospheres instead of 1 atmosphere. And again, you can refer back to the Reynolds video to watch step by step how you can do that. Okay, so now we have the properties. We can jump into the next part of the analysis, which is let's find what's Reynolds, right? Because if we know Reynolds, then we know if this is a laminar or turbulent flow, and that's going to help us figure out what is the equation we should use. So Reynolds is 2 times 1.1133, which is density. My velocity, which is 30 meters per second. And we're going to do L, okay? So we're going to do the length of the plate, which is 0.5 meters. And the density is 2.16 times 10 to the minus 5. So Reynolds is 1.44 times 10 to the 6th Okay, so this is a turbulent, it's a turbulent flow that we're seeing. But the question now becomes, is this turbulent throughout, or is it turbulent just in the beginning, or does it become turbulent halfway? So I don't know. This is time sensitive 5th. Okay, this is a horrible 5, but it's a 5 nonetheless. Okay, so this is the part in which you have to do the analysis. Okay, so what I'm going to do is, there's multiple ways you can go about this, but what I'm going to do is I'm going to find what is my X critical. Okay, in other words, at which point does the flow become turbulent? Okay, and to do that, well, what I'm doing is I'm using this equation, obviously, and then I'm solving for X, right? Instead of having 0.5, I'm going to solve for a known there, and I'm plugging in my critical Reynolds there. And I got 0.17 meters when I do that. Okay, so we have a, so or if you wish, 17 centimeters, right? So we have a 50 centimeter plate, and at 0.17, 17 centimeters, this guy becomes turbulent. So let's look at our drawing and let's have a little analysis. This is 50, so actually I think these guys are here probably because of that already. Right, so if this is halfway through, that will be 25, and then like maybe about a quarter will be my 17 centimeters. So if I'm breaking these guys down, this would be the part in which I would have laminar flow, and that's where laminar flow is exchanging my energy with the plate, and then from that point onwards, it will be turbulent flow. So with this, we have to choose. We have different equations to choose. We have one that will be the equation for laminar flow completely, one for turbulent flow completely, and one that has the combined effect for the entire plate. Okay, so you can have a look. I'll pause the video and let you have a look and decide which one you would use, and then we can talk about it. So you should have ended up eliminating all others and being left with these two here. Okay, and then the difference between these two here is that on this one here, we're assuming turbulent flow is dominant in our plate. And on this one here, the idea of this one here is that it has a small tweak, and it actually takes a bit more into account the effect of the laminar part in the beginning. So you notice the only difference between the two equations is this negative 871. And that number there is to, let's say, take into account the influence of the laminar part on it. Okay, so all this other things satisfy all the other criteria are satisfied, and for these two equations. So it's up to your interpretation to do it. Now, would you guys say that laminar has an influence in this system and use the bottom one, or do you think turbulent, because turbulent is taking about 3/4 of this, you should use the top one?
Well, I'd think the top one, but I don't really know that much about it yet, so
No, but that's good. But what's your true thought?
like using the top one because the majority of it is turbulent. So
The majority of it is turbulent. Any other arguments for or against that?
I would also agree that you should probably use the top one.
You also do the top one. Okay, so this is what I'm saying. Like, it's up to interpretation, and that's why it's extra important for you guys when you're solving, when you're dealing with these problems, to actually explain your train of thought of or why you chose one thing over the other. Okay, because for us, as we're correcting it, as we're marking it, we need to know if the student just randomly guessed and picked an equation, or he actually had this train of thought. That can be a difference from getting a 0 or actually getting a good mark for something. So I'm going to do the bottom one. Because I'm going to say that in spite of the turbulent dominating, which we all agree it does, because there's 1/4 of laminar, that's actually a considerable bit. So I'm going to consider that minus 171. If, however, you guys came up to me and said, "Oh, 3/4 of it, 3/4 of it is turbulent. Therefore, because it's dominant, I'm going to choose the top one. All right. If you do that explanation, you most likely get the mark 2. Okay, because like I said, this is up to interpretation and understanding how the different equations will influence your system. Okay, so I'll choose this bottom one, and I've plugged the values here already for us. Okay, I'm doing average Nusselt. This is a constant. Then Reynolds, we have calculated already to be 1.44 times 10 to the 6th. Prandtl we got from the table, and I got a Nusselt, an average Nusselt of 2006. Okay, so that will be my average Nusselt. Remember, a Nusselt doesn't have any units. Once I have Nusselt, finding my average convective coefficient is straightforward, right? I just need the conductivity of my fluid, in this case the oxygen one that we had from the table in the beginning, and the length, the L, which is 0.5 or 50 centimeters. So I get the H to be approximately 120. I would invite the people that were arguing for the top one to also solve it for the top one later, and seeing how different it would be from this. It's not going to be that different, okay? So again, there's a lot of interpretation, a lot of different possibilities when we get to this part of the subject. And just to pick your brains a bit more, there's more equations than just these two. These are the two that, from the options that I gave you, you could end up using. Okay, so once we have our H, then everything becomes trivial, right? Because once we have H, again, the end part of it, let's do big red. The Q that is the thing that we're looking for, right? The Q is simply Newton's law of cooling. And now that we did this whole rodeo to be able to find the H, then we just need to apply it, right? So 120 will be our area. Well, our area is 50 by 50, right? So 0.5 times 0.5 or 2 squared. And our difference in temperature is 127 minus 27, or just 100 Kelvin or Celsius. Okay, so this turns out to be 3,000 watts if you approximate it like I did. Okay, so once again, I welcome you guys to have a go with the other equations, see how different your answer would be. Okay, but if you are explaining what you're doing, you're way better off than just guessing and pointing equations up there.